The latest images from the James Webb Space Telescope have profoundly impacted the scientific community, providing a fresh perspective on our understanding of the universe. These new photographs revealed a startling truth. Our ongoing comprehension is insufficient to fully grasp the vastness and intricacies of the early universe. The theoretical framework regarding the origins of the cosmos seems to hit a boundary that forces us to reconsider our hypotheses. This drives us to pose new theories about the universe's formation, prompting questions such as how the universe took shape, and why these new findings are challenging even the most seasoned astrophysicists to delve deeper into the Big Bang and the continuous developments surrounding these revelations. It is crucial, however, to explore the very essence of the Big Bang itself, stepping away from popular assumptions. Contrary to common belief, the Big Bang was not a conventional explosion within pre-existing space. Instead, it was the very fabric of space itself that began around 13.8 billion years ago, along with time and matter. This concept represents a key milestone in modern physics and cosmology. A phenomenon known as a quark describes a region where gravity is so intense that the curvature of spacetime becomes infinite. Today, after billions of years since the universe's inception, we recognize that our cosmic home exists within a broader collaboration. For scientists, this represents a critical segment of the universe, as its existence and constant evolution are fundamental to understanding its current and future state. The universe is not expanding into pre-existing space. Rather, space itself is continually expanding, stretching outward. According to traditional models, the first stars began to shine roughly 200 to 300 million years after the Big Bang, marking the end of what is known as the Dark Age. This was the period when the first luminous objects began to cluster, forming early structures. However, the rapidity of galaxy formation during this era remains one of the greatest mysteries in cosmology. A significant breakthrough came in July 2022, when the James Webb Space Telescope captured images of the universe's distant past. Scientists revealed that the telescope had identified galaxies, many of which had formed approximately 300 million years after the Big Bang. However, compared to the majestic structures that arose billions of years later, these early galaxies were much smaller and less developed. This finding aligns perfectly with the prevailing scientific model, which suggests that the density of matter in the early universe was insufficient to form galaxies on the scale of those we observe today. The discovery began with the identification of 6 extraordinary redshifted points by the James Webb Telescope. This finding led to one of the most significant cosmic revelations in recent times. Despite these newly discovered cosmic entities sharing an age similar to present-day galaxies, they are nearly as massive as our own Milky Way. This has posed an intriguing puzzle for Big Bang cosmology. After reviewing a series of images collected by the telescope's near-infrared camera, scientists identified these early light sources. By analyzing their redshift, experts confirmed that the light from these objects took over 1 billion years to reach Earth. Consequently, these structures were already in existence between 570 and 700 million years after the confirmed Big Bang. Upon analyzing the characteristics of these objects, scientists concluded that the Webb telescope had captured images of 6 early cosmic entities. Astonishingly, these galaxies were so large that they defied traditional cosmological assumptions. Instead of discovering the expected smaller galaxies, the telescope revealed systems that were nearly as vast as our own Milky Way, despite forming so early in the universe's history. If further examination of the data collected by the James Webb Telescope is pursued, these gravitationally bound systems were already over 10 billion times the mass of the Sun, with one system reaching a remarkable 10 billion solar masses. Yet, even in this context, the mystery remains unresolved. The discovered objects challenge almost every established cosmological theory. Even if, by some stroke of luck, one of these galaxies proves to be authentic, it would call into question the previous assumptions made to explain the formation of these structures. For such galaxies to exist, the density of matter in the early universe would need to be several times greater than previously assumed. Another equally puzzling explanation is the possibility that these galaxies formed in a way that remains entirely unknown to us. These groundbreaking discoveries and the debates they have sparked will likely fuel a re-evaluation of the Big Bang theory itself. Many astronomers with alternative viewpoints are frustrated by these new findings, and their perspectives frequently find expression in scientific publications. Even those who question current models are often labeled as mistaken or extreme. Nonetheless, it is clear that even those who continue to defend the Big Bang theory are faced with persistent unanswered questions. These include matters such as how, 13.8 billion years ago, something seemingly arose from nothing. Can something truly emerge from nothing, or did some external event or mechanism trigger this occurrence? Or perhaps it was all a random accident. Stephen Hawking once argued that time itself, as we understand it, began with the Big Bang, meaning that this process could not have been initiated by any external cause. A similar question arises regarding the uniformity of radiation and matter throughout the universe. Regardless of where we look, whether near or far, we find similar densities and distributions of structures, nebulae, and radiation across the cosmos. Current physicists explain this phenomenon through the theory of cosmic inflation. However, some specialists expand on this theory, proposing a model of turbulent expansion. According to this view, the expansion has created specific regions, or bubbles, while leaving other areas unaffected. This theory suggests that multiple universes could exist, each with its own distinct set of physical laws. This leads to an intriguing question. What if our universe does not represent the totality of existence? More specifically, what if another universe preceded our own? In this case, the Big Bang might be part of a larger, cyclical process. From this perspective, our universe is just one bubble within a more intricate structure. This model supports the idea of an endless cycle of cosmic collapse and rebirth. However, this is not the only theory within cosmology. Aside from the classical view of the Big Bang, an article published in NASA's Big Time in 1955 proposed that there might never have been a Big Bang at all. In this view, the universe has always existed in some form, and the apparent expansion is simply a result of the consistent evolution of matter over time. An equally fascinating hypothesis stems from the realm of quantum physics and string theory. Certain experiments have suggested that our universe and everything within it could be a projection or a higher dimensional simulation. While this may seem more fitting for a science fiction narrative, it has connections to the Kardashev scale, which measures a civilization's ability to harness energy. A Type 3 civilization, capable of utilizing the energy of an entire galaxy, could theoretically generate a perfect simulation. However, proving the existence of such a reality remains a highly complex and speculative endeavor. Exploring the origins of the universe leads us into a realm of profound mystery and ongoing scientific exploration. The recent images from the James Webb Space Telescope have reignited debates about the fundamental nature of our existence, testing established theories and compelling researchers to reconsider core aspects of cosmological knowledge. At the heart of this inquiry lies the concept of the universe's foundation, a foundation of modern cosmology. According to this prevailing theory, approximately 13.8 billion years ago, the universe emerged from an intensely hot and dense state, rapidly expanding to form the space-time and matter we recognize today. This grand event was not merely an explosion within pre-existing space, it marked the birth of space itself. The idea of a singularity, where gravitational forces are so extreme that space-time becomes infinitely curved, helps support our understanding of the universe's early moments. However, the James Webb Telescope's discovery of early cosmic structures challenges our assumptions about how rapidly such structures could form in the early universe. The galaxies captured in these images, appearing large and advanced so soon after the Big Bang, prompt a reevaluation of our models of cosmic inflation. According to the prevailing theory, inflation occurred within fractions of a second after the Big Bang, causing the universe to rapidly expand. This expansion is thought to explain the uniformity of the cosmic microwave background radiation observed throughout the universe. Yet, these recent findings suggest that the universe's early development may have been more complex than inflationary models can currently explain. The formation of galaxies visible through the Webb telescope forces cosmologists to reconsider the processes and timing involved in the early universe's evolution. The vastness of these galaxies challenges our previous understanding of matter density and the rate at which structures could form. Additionally, the discovery of these early galaxies raises critical questions about dark matter and dark energy, two mysterious substances that constitute most of the universe's mass and energy. While dark matter is thought to provide the gravitational framework necessary for galaxy formation, the properties and distribution of dark matter in the early universe remain uncertain. In light of these new astrophysical discoveries, theorists are exploring alternative cosmological models that challenge the conventional Big Bang view. Some suggest that our universe is just one of many in a vast multiverse, each with its own unique physical laws and constants. These emerging theories, driven by advances in string theory and quantum cosmology, offer a vision of a far more interconnected and complex universe than we have ever imagined. One growing theory is that of timeless inflation, in which universes continuously emerge from an ever-expanding space. According to this theory, our universe may be just one bubble in an endless sea of others, each with distinct physical properties. However, the real challenge lies in finding observable evidence to support these speculative ideas, as they push the limits of our ability to observe and test these cosmic scenarios. Another fascinating hypothesis suggests that our universe exists within a simulated reality, akin to a computer-generated simulation. This concept draws parallels with advancements in artificial intelligence and computational science, where simulations can replicate complex systems with remarkable accuracy. If this hypothesis is true, it could radically alter our perception of reality, raising profound philosophical and scientific questions about the nature of existence itself. The ongoing exploration of cosmology and the universe's origins delves deeper into the mysteries of existence. As the James Webb Space Telescope continues to provide unprecedented images and data, it not only expands our knowledge but also forces us to confront the limitations of our current understanding. With each new discovery, we are presented with a plethora of questions that challenge the assumptions we have long held about the cosmos. These challenges push scientists and theorists to think beyond conventional models and to reconsider how we perceive the universe, its birth, and its ongoing evolution. For instance, the detection of massive galaxies so soon after the Big Bang calls into question our understanding of galaxy formation. If these early galaxies were capable of reaching such sizes, it suggests that the processes governing the early universe were far more complex than previously thought. The speed at which matter clumped together to form large-scale structures challenges the timeframes proposed by traditional models of cosmic evolution. As a result, new theories must be considered, exploring the possibility that the universe may have experienced rapid phases of evolution that were previously underestimated. The role of dark matter and dark energy in this process remains one of the most significant unknowns. These mysterious components of the universe, which together constitute around 95% of the cosmos, are essential to our understanding of how galaxies and other cosmic structures formed. However, the exact properties and distribution of dark matter and dark energy in the early universe are still elusive. The early galaxies identified by the James Webb Space Telescope could potentially hold clues to the nature of dark matter, offering new insights into its distribution and influence on the formation of matter in the universe. One of the more radical theories emerging from this research is the idea that the universe we observe may be just one of many in a vast multiverse. In this model, our universe is a single bubble in a larger cosmic foam, with each bubble representing a separate universe with its own set of physical laws. This concept draws from developments in string theory, which suggests that the universe is made up of multiple dimensions beyond the familiar three of space and one of time. These extra dimensions could provide the basis for the existence of parallel universes, each with its own unique properties and characteristics. If this theory is correct, it could have profound implications for our understanding of the nature of existence and the fundamental laws of physics.